if you look at history, and there is a science called paleoclimatology, the levels of carbon dioxide on the planet have been significantly above 420 parts per million. Actually, they've gone up into the thousands, and at that time, the planet was lush. It was like a big jungle because carbon dioxide is the food for plants, and it certainly didn't kill anything.
This is Climate Debrief, brought to you by the CO2 Coalition. I'm Angela Wheeler. Today I'll have a conversation with Dr. John Dale Dunn. Dr. Dunn is a board-certified physician with decades of experience practicing as an emergency physician in Brownwood, Texas. Dr. Dunn is also a non-practicing attorney admitted to the bars of multiple states with 35 years of legal experience. For more than 25 years, Dr. Dunn has engaged in rigorous research, scholarship, and advocacy concerning environmental science and policy. His primary areas of focus include human toxicology, epidemiology, scientific evidentiary standards and legal proceedings, research methodology, and ethics. Dr. Dunn's distinctive combination of medical practice, legal training, and long-standing scholarly work in toxicology and epidemiology provides a grounded, evidence-oriented perspective on complex environmental and policy questions. Dr. Dunn, thank you for lending your expertise to our Climate Debrief audience. Today we'll be discussing a presentation you created for Climate Debrief entitled Science Concepts and Methods, Challenging Linear No-Threshold Theory, From Radiation to Climate Policy, a Critique. Dr. Dunn, we're diving into your work on science concepts, linear no-threshold theory, and its surprising links to climate policy. Tell us, how did you get from toxicology to net zero?
The linear no-threshold theory developed as a result of research with regards to radiation, which is, everybody knows a little bit about radiation. It's all over us. Cosmic radiation comes from the stars, and the radiation that we're talking about that's important is the kind of radiation that people experience here on the planet. So you get cosmic radiation from the space, but there are other sources of radiation in the soil, in minerals, and obviously the big one is uranium and radium and the exposure to radiation is something that can produce dangerous changes in the body because radiation can damage. There are three basic forms of radiation. The study of linear no-threshold was a radiation study, and it was done originally with fruit flies because they have rapid reproductive patterns, and you can study things that happen to fruit flies if you expose them to radiation. The problem is that linear no-threshold was the result of cheating in radiation biophysics, which is the study of the effect of radiation on human and other living things. And a guy named Herman Mueller started off doing radiation theory studies on fruit flies because he wanted to show that radiation might be the mechanism to produce evolution, which requires a certain amount of change in genetic material in living things. And what he claimed in his research was there was no threshold that any amount of exposure to radiation produces impacts on the human body or the human organism, and that no threshold theory was used to produce a pattern of regulatory activity that started with the idea that there is no safe level of radiation. It became a theory that was used for toxicology in general, so that if you could find some kind of damage from any level of exposure, a high level obviously is the one that you're looking at, then toxicologists said, well, that must mean that there is no safe level. There's going to be an impact from anything that we consider to be a toxin, all the way down to net zero, which is the goal of regulatory activity with regards to things that are deemed to be toxins, whether it be radiation or, in the case of other kinds of things, small particles in the air, ozone. Non-threshold theory, the linear non-threshold theory, has been a basic, and it's combined with another thing that...
In your presentation, you mentioned Paracelsus and his famous principle, the dose makes the poison. How does his 16th century insight still hold up against modern risk models?
Paracelsus was a physician in the way that a 16th century physician could be. They didn't know a whole lot of things about a lot of things, but Paracelsus studied the question of what harms people. Doses make the poison is what he concluded, because what he found was that at certain levels of exposure there isn't any effect that he could see, and at higher levels it was evident that there are things that cause damage. Paracelsus gave us what was and still is the basic idea in toxicology. Yes, there is a threshold. Below that threshold, the toxin that you're studying certainly is not going to cause any damage. And above the threshold, when you find a damaging level, it's based upon the dose or the exposure of that particular toxin to whatever you're studying, whether it be bugs or birds or human beings.
You describe linear no-threshold theory as assuming harm at any dose if it's harmful at high doses. Can you explain in plain terms why you call this approach junk science? And please give an example of where it originated.
It doesn't take a lot of brains to say that, a high level of exposure to something may cause damage, and toxicology is all about the study of what's causing damage. But the junk science part is to say there isn't any level that's acceptable, so that you can regulate something all the way down to zero, even though there are obviously levels where an individual thing that you're studying that might be toxic at a high level are not going to be toxic at all. And I'll give you a good example. Dust in the air is not toxic in the ambient levels that we have in the atmosphere. But a whole junk science theory developed around the idea that all you have to do is have some amount of small particles in the air and you will get some effect that is horrific. So they claimed that the small particle levels in the air in the United States were killing more than 300,000 people a year. Annual death rate that's almost equal to the death rate caused by cancer. And that's just plain junk science. There is no way that the ambient small particle levels were justified. They justified that kind of a claim. But they did what amounts to nothing more than cheating on population studies in order to make the claim, and then they could push for the regulations.
Hormesis flips the script. Low doses can actually be beneficial. What kind of real biological examples have convinced you that hormesis is more accurate than linear no-threshold theory for many exposures?
Hormesis is a unique aspect of toxicology study because there were a lot of toxicologists that didn't even worry about whether there was a hormesis level. But I'll just give you the one that has to do with radiation. In fact, low levels of radiation exposure reduce the number of people that get cancer that is attributable to radiation. So, in fact, there are certain levels of radiation that are not necessarily just not toxic, not damaging, but in fact, they may have an impact on the cells of the body that increase the resistance to the development of cancer. And that's where a hormetic level appears. In the case of other toxins, I guess the best way for me to talk about it is in the business of pharmacology, we know that there are levels of drugs that produce good effects, and then there are levels of drugs where they produce bad effects. And the good effects are in the hormetic range, and then at a certain point, they can become essentially harmful. Now, that's the best way for me to explain it to people who don't necessarily think about it in terms of, well, what's the level, what's the dose of a toxin that's toxic? Well, you have to actually individualize it. And I'll give you one example that's it's an exaggerated example, but it's something that you might consider to be a good example. Obviously, there's a proper level of water in your body. If you get, for some reason, obsessed about drinking water and you drink too much water, the amount of water in your body can increase to the point where it causes a brain dysfunction that is produced by what is nothing more than over-soaking the brain tissue. So that's a good example of something that you normally wouldn't think of as toxic at all, but at a certain level of exposure, the amount is enough to cause damage.
Looking at this conceptual diagram comparing linear no-threshold theory, hormesis, threshold, and other curves, what does the epidemiological evidence actually show at very low doses of radiation or stressors, and why does hormesis fit the data better?
Well, the epidemiological evidence is, we have first of all understand what epidemiology is. It's a study of populations, and you can study populations in an uncontrolled manner, or you can study populations in a controlled manner. The population studies that the junk scientists like to work in are the population studies that are uncontrolled. So what you do is you gather data on a population in a particular geographic area, let's say the country of the United States or the state of Texas or whatever you want to do. And then what you do is find out what their ambient levels of exposure are, or what their levels of exposure are by what they eat, or what may be the particular toxin that you're studying, something that's in the water, or something that's in the air, or something that's in the food supply, okay? So doing the study, you try to match up exposures for this population that's uncontrolled, it's just out there, and then you look for death rates. Well, in the range of what you call randomness, there's a certain death rate that you can expect when it's out of order. For example, if it varies a little bit above or below the death rate that should be for that population, that's just the result of what is known in the business as randomness. If you try to find data where the random variation in the death rate is elevated, and then match it up with what you say is the toxin that you're studying to see whether it causes an increase in the death rate, you can easily do that. And if you're a cheater, what you can do it is find it in small amounts that are more than the regular rate of death, and then you can point to that as proof that there is a lethal effect of a particular toxin. Well, there are some rules about how to do that so that you don't cheat, and we're going to talk about those in a little bit. Hormesis is nothing more than identifying the area of dosage or exposure where it appears that there's a beneficial effect of something that at other levels is toxic. And the perfect example is radiation. Low levels of radiation are actually healthy and reduce the rate of cancer in the studied population, where you know for a fact that excessive doses of radiation clearly produce cancer.
Dr. Dunn, here you draw a direct parallel. Net zero treats CO2 emissions the same way linear no threshold theory treats radiation, no safe level. How did this zero tolerance mindset migrate from radiation policy into climate change discussions?
Think about this. Carbon dioxide is essential for life. For anybody to say it's a toxin is to say, whoa. You're telling me that the essential element or the essential molecule for plant growth, which is what we depend on in order to live, is toxic? Well, I guess maybe then we might as well just close it all up and shut down the human population, because they're all dependent upon what happens with regards to carbon dioxide. So instead, what we could do, maybe if we were sensible, we could say, okay, we know that CO2 is present in the air in what is called a trace amount. It's less than 1%, 0.04%, which is 400 parts per million, and it's slightly above that now. And there was a point in time, not long ago, when it was down in the range of the high 200s, low 300s, which is critical almost to the point where plants can't survive. It's not enough carbon dioxide in the air for them to be able to grow. So the level where it's essential and it can't go any lower is around 300 parts per million. Well, we're up to 420 parts per million, and the whole crisis of carbon dioxide emissions is built on the theory that if carbon dioxide increases, it's going to cause the planet to get warmer. And the carbon dioxide that we're talking about is the same carbon dioxide that is very helpful if you pump it up to 800 to 1,000 parts per million in greenhouses. Makes plants grow better. And at that level, there is no kind of toxic effect on humans. So the only thing that can happen that will make the regulatory crazies get nutty is they say, okay, yeah, but once it gets past 400, it's going to start the planet to warming. And we know that because of what's called the greenhouse gas effect. And so we need to make sure that carbon dioxide does not go above a certain level. Otherwise, the planet's going to boil over and we're all going to die. Well, if you look at history, and there is a science called paleoclimatology. Looking back at the planet, the levels of carbon dioxide on the planet have been significantly above 420 parts per million. Actually, they've gone up into the thousands. And at that time, the planet was lush. It was like a big jungle because carbon dioxide is the food for plants. And it certainly didn't kill anything. Carbon dioxide, the only way that carbon dioxide kills humans in the breathing, in the atmosphere that they breathe, is if it gets above 8,000 parts per million. It starts to crowd out the oxygen. In the atmosphere of the planet, nitrogen, which is an inert gas basically, but it's essential for plant growth. Nitrogen is something that combines with other things to create proteins, and proteins are essentially a part of living things. So nitrogen is present in about 80% of the atmosphere. Oxygen is a little less than 20%, and then there are the rest of the things that are in the air, like argon and carbon dioxide and methane and some of the other gases, are all there in trace amounts.
This concludes part 1 of my interview with Dr. John Dale Dunn. We hope you'll join us next week for part 2.
Thank you for joining us on Climate Debrief. Executive producer is Angela Wheeler. Producers, Ethan Audie and Scott Wheeler. You can find more episodes of Climate Debrief at co2coalition.org.